Okay, sorry about that, guys. So that's example-wise, when we talk about vectors, they are very similar to scalars. So the vector of distance is called displacement. So if we're talking about distance, displacement is a vector of, it's how far away you are from where you started. So this would be an example of it. You might say 13 meters, but then you have to give a direction. So you might say north, okay? Or northeast, or north 20 degrees east, or whatever, things like that. Okay, when we're talking about speed, speed has a vector quantity that's called velocity. So the example of speed would be velocity. Okay, so if you're going 50 kilometers an hour, you just put a direction on it. So 50 kilometers per hour, let's say south this time. So that's basically the only differences. Now the main ones that we look at in motion is we look at distance and speed as scalars, displacement and velocity as vectors, and we also add in acceleration as a vector. Acceleration is how fast your speed is changing, or how fast your velocity is changing over time. Okay? So that's our first little piece. That's our first objective for today. So the next thing we want to do is we want to spend our last 20 minutes or so here looking at how we combine vectors. So vector addition or subtraction. Subtraction and addition is the same thing in physics. If you're subtracting vectors, you just flip the vector around. If you're adding them, you add them together. So we're going to look at adding vectors. Okay? So the first thing I have to show you, and many of you probably are familiar with this if you've taken math at a grade 11 level, is how you state vectors in direction. There are a couple different ways to do it. Now the most common way is the north, south, east, west grid way. Okay? So that's what we're going to go first. This is the one that's used 90% of the time, and it's also, by me, it's almost used 100% of the time when I do my problems and things like that. So that's our next little piece here. So we're going to look at, we're going to call it the north, south, east, west, and I'm just going to go north, south, east, west, like that. Method of presenting vectors. Okay, so the general idea here is to have your north, south, east, west grid on here. So if we draw that, hopefully you guys, okay, it's just like the quadrant system in pre-calc. Okay, and we consider that this is our north line and our south line is here. Right? And then we consider that this is our east-west line here. Now, there is a little bit of an issue with myself. I tend to be somewhat dyslexic in my brain. So I'll say west sometimes and draw something to the east. You know, I don't know why I do that. It just happens. So if I do that, say, hey, isn't that the wrong way? Okay. If I make mistakes, let me know. It happens. I used to consider myself perfect, but I'm not that. So if you see something like that, make me aware. So how does listing a vector work? So first of all vectors are going to start from the origin in the north, south, east, west way of presenting the vector. So a vector is usually drawn as an angle, okay, in one of these areas. So let's use an arrowhead to draw an example vector. I'm going to draw one here in green. Okay, so let's say it's over here. And let's say that this is 28 centimeters. And that we know that this angle here from the west line has been measured. Let's say it's 21 degrees. Okay. Oops, I got all these tabs open. Okay, so the way of presenting this is just stating, starting from one of these lines, either the south line or the west line. Now, because the angle is here, I'm going to start from the west line. So basically, we say, let's call this vector A. Now, vectors are usually listed with a capital letter like that. I usually put a line over mine, but in textbooks, like we don't have a textbook for this class, but if you are using one or doing some extra physics on your own, they usually put them in bold lettering, capital, dark, bold lettering, and that also means vector. Okay? So we could say that vector A is 28 centimeters. That's our magnitude. And then we state our vector direction, and we use square brackets, generally speaking. Some people use the squiggly brackets, you know, the fancy ones. That's okay too. But I use square brackets. And what we do is we state the first direction line that we have, which is west, 21 degrees to the south. Now, all vectors can be measured. All vectors are in one of the northwest quadrant, the southwest quadrant, the northeast quadrant, or the southeast quadrant. So they can always be measured from two spots. You can measure from the west line here in this case, or you could measure from the south line. If you were to measure from the south line first, this angle here we know is 90 degrees. So we actually know what this angle is as well. So we could state that in another way. We could say that this is 28 centimeters. And then instead of starting here, we could start on the south. And we know 90 degrees minus 21 is 69 degrees. And you're going up towards the west line. So that's the north, south, east, west way of presenting a vector. Okay? Okay, I'm going to draw one, and then I'll get you to write down what you think it is, and then I'll do it here in a couple minutes. So I'm going to draw an orange vector, and then list the two ways that you can present it. Okay? So let's do an orange vector here. Whoops, let's get that vector line here. Okay, so let's do one right here. Okay, and let's say that this angle is measured here. We'll call this vector B. We'll say that this is 36 millimeters. And we'll say that this angle here is 78 degrees. Okay, I'll give you a minute or two to write your guess, and then I'll write, or your what you think it is, and then we'll do it. And that's our second major point of how you present the vectors. Now, we're not going to be using this until we do something called component vectors, okay, which will be later. We'll probably be spending all week on vectors. We probably won't do any lab work until next week sometime when we get into doing some motion and some graphing of motion. So if you're in your classroom there, what are you going to need for next week in terms of materials? One good ticker timer would be handy. We have two here in Vanguard. One good ticker timer to find, and it would also be helpful if you had a dynamics cart, and I'll show you what those look like probably at the beginning of tomorrow. So then you can go digging around and finding them. And like I said, if you don't have the stuff, we'll always take results from Vanguard and post them up online, and you can do the analysis using other people's results. Not as much fun, but it can still be done. Okay, so what are these two ways of presenting this vector? So B here can be presented two ways. You could say that this is 36 millimeters. And you could say, firstly, it's south 78 degrees to the east. That's one way to present that. South, then back up towards the east, 78 degrees. Well, and then we could also use this little piece here if we figure out what this is. 90 minus 78, that's 12 degrees. So you could present that as 36 millimeters east first, and then 12 degrees down. Sorry, I should put a degree in there. To the south. Okay, so not too familiar. I think if you've done some sine law and cosine law questions in math back in the old days, you're probably familiar with that, right? Now, if you haven't done those because you're in grade 11 and you're taking physics 30, or if you are just taking physics 30 and you did foundations only, that's fine. When we get into that method and I start using those techniques, we'll be reviewing how they're used and how they're done. Okay, so that gives us about, it's about 40 after. I want to go to about 10-2 because I need some transition time. What we're going to do now is we're going to look at vector addition. So we're going to look at the first one, the easiest possible one, and we're going to look at perpendicular vectors. So if we look back at our initial idea for today, we're going to do some collinear, and we're going to look at an example of perpendicular and go from there. So I'm going to flip the page. Collinear vectors are the easiest of all. And so this area is called vector addition. Okay, and we're going to look at four major types of vector addition. We're going to look at collinear, perpendicular, and skew vectors in two ways. Skew vectors in terms of cosine law and sine law, and skew vectors in terms of components. So when we do skew vectors, we're going to be looking at two different methods of how we would do it. So if the math is not there in one way, you'll be able to do it in another way. So collinear is the easiest. These are vectors along the same line of path. Okay, so the first thing and the most important thing that we want to put in here is the rule here. When adding vectors, okay, it's pretty simple. The second vector's tail starts at the head of the first vector. Okay, and we'll put it in quotation marks. Right? So the tail of the second vector starts at the head of the first vector. Okay, and remember, whenever we're doing vectors, everyone, you always have to put a direction there. Okay, so don't forget to put a direction there. And sometimes directions are just positive and negative as well. If you're doing collinear vectors, sometimes you're going backwards or forwards. That's still a direction. It doesn't always have to be north, south, east, west. It could be up or down, negative or positive, right? Forward or backward. Those are also considered directions. Okay, so let's do an example of collinear, and then we'll do an example of perpendicular, and that is what we'll call a date. Okay, so first one we're going to look at is collinear addition. Okay, so let's say that we're going to do 13 meters north plus 8 meters south. That's just our elementary bill. My typing is a little slow because I'm rusty. All right. I guess I should put myself up here so that you can see that what I look like in case you run into me and you want to say hi or something. All right, so what we do is we draw it out. This one you don't even really have to draw out, but because it's so simple, but we'll do it anyway. So you always have a starting point. So I'm going to put a dot for my starting point. Okay, we'll just use black here. So there's my start. Now I don't need the grid for this. I'm just going to draw a vector to the north, 13 long. And then I start there's the head of the first vector. The second vector is going to come down 8 south. Here, I'll use a different color so we can see it over top. Okay, so there's our finish. So basically we label this up. We have a 13 meter orange one there and an 8 meter green one there. So what's left? Well, here's our resultant vector. There's our start, there's our finish. So what's left here? 5 meters. And there's our start, and we're 5 meters north. And that's it. That's how you do collinear vectors. Pretty easy. Okay, as long as they're in the same line. Okay, so I'm only going to do one on that one. We don't spend a lot of time on that. It's very seldom in physics. We're usually looking at movement in 2 dimensions at least, sometimes 3. Okay. We do not have the capability to do 3-dimensional vector algebra in high school, but if you take calculus, some of you guys might be doing that next term, calculus is very handy when it comes to motion. Velocity is the derivative of displacement, a displacement equation, and acceleration is the derivative of velocity equation. So that's kind of how calculus works. Because as you'll see later, they're actually slopes. Okay, so I'm going to do a perpendicular vector example, and that's probably as far as we're going to get today. I didn't get as far as I would like to, but that's okay. For the first day, not bad. Okay, so the second type we're going to look at is we're going to look at an example of perpendicular vectors. So an east-west vector and a north-south vector being combined together. So let's say this is B, and recall these perpendicular vectors. Now, some of you guys might have done some of these in grade 10, in grade 10 science, okay? Or maybe even in physical science 20, you might have done them if you did some motion there. But I usually do a little bit of it in grade 10 science. So it's been a few years for some of us. Okay, so let's do an example of it. Let's just do a plane flying in an air. So let's say a plane, not a planer, pointing due north, is flying 325 kilometers an hour. So that's a vector because it gives us a direction, even though it's not in the same way that I presented it all. With respect to the air. Now, I use this to represent with respect to. Okay, so if you see that abbreviation, it's because generally speaking, physics guys are lazy. Okay, they don't like writing stuff. Or maybe it's just me, I don't know. Could be either or. Okay, so with respect to the air, that means it's moving 325 kilometers an hour in the air. Okay, through the air. Okay, and then there's a wind. Okay, so period there. The air is moving due west at 80 kilometers an hour. Okay, so that's the air movement. So what is the velocity of the plane with respect to the ground? Yes, there is a fair amount of math in physics, right? But there's also a fair amount of doing labs as well and stuff like that when we get in there. So, okay, what is the velocity of the plane? And I'm going to go with respect to the ground. Okay, so we're going to combine the two vectors, the west vector with the north vector. I'm going to draw it out in a right triangle, and we are very familiar with right triangle work. You first get introduced with Pythagorean theorem in grade 8 math, and then you move on, and right around grade 9 or 10 you start talking about sine and cosine. Okay, so if we draw this out, here's our starting point. So I always put a dot where my start is. Okay, and we're going to go, and we're going to be flying due north. So we're going to draw a nice large due north vector in here. Okay, and that's 328 kilometers an hour, or sorry, 325 kilometers an hour. Okay, and then remember the rule, the second vector's tail goes at the head of the first vector. So we're going to put the wind up here going to the west. Now the wind, I'm going to put it here as a vector, and I'm going to put it, it's going to be shorter because it's smaller. So that would be my wind. Okay, so with respect to the ground, if we put in our 80 kilometer an hour here, okay, so there's our diagram. Now where's our resultant vector? Well, our resultant vector starts at the very beginning and ends at the very end of our diagram. So here's our starting point right here, the dot. Here's our finishing point. So our resultant vector, which is what we call the vector when we combine the two together, is the resultant. Okay, that's a traditional term. You could call it the summative vector or whatever you want, but I usually use the word summative, resultant. And usually what I do is I stick it in like this. Okay. Okay, now we can see that it went northwest. So we need the size of the vector, and we need this little angle down here. So I'm going to put an angle measure in there in green. We're going to need that angle to get the direction. It's going to be north and then west, or you could do west and then north if you wanted this angle down here. But I drew it this way. You might have drew the wind first and then the plane with respect to the air. So again, there's another way to draw this. You could have went this way and then up, rather than up and then over. Both of them will give you correct answers. Okay, they both arrive at the same spot. How do you get this? Here, resultant vector, which we'll call r. Well, this squared plus this squared equals that squared. So we know from Pythagorean theorem that 80 kilometers per hour squared and 325 kilometers an hour squared is going to give us our squared, or our resultant squared. Take your calculator out. I actually have mine worked out on screen here, so I don't really need to do that, but I'm going to do it anyway. So 80 squared, go ahead and give it a try, 80 squared plus 325 squared. Okay, we got 112.25 equals r squared, and then we square root that to get our magnitude. So if I square root that, okay, significant figure wise, it's kind of weird. I should have put this as 80.0 so that we had 3 in each. So we'll talk about how significant figures. We're going to do 3 significant figures. I should have put 0.0 there so that I had 3 and 3, so that we knew that that was an significance. So this is 335 to the 3 significant figures, kilometers per hour. There's our magnitude. That's not our vector. That is just our scalar value. So we need this angle here. So now we're going to get the angle. The inverse tan of the opposite over the adjacent, 80 over 325, equals that angle. Okay? Now if you want to write tangent out and then do the inverse tan, I kind of did it one step. You could write it tan theta equals 80 over 325 and then do the inverse tan, right? So then you take your calculator out. Make sure your calculator's in degrees. We're not using radians in physics. We're using degrees. If we do angular velocity, we might use some radians. Okay? So I go inverse tan or second function tan on my calculator. And then I go bracket 80 divided by 325, close the bracket. Now, if you have a backward calculator, like one of the smaller ones, sometimes you have to go 80 divided by 25 inverse tan. Forward calculator, you go inverse tan, 80 divided by 25 equals. So mine's a forward calculator. It looks like that. I hit equal, and I get 13.8 degrees. So I'll round it off to 14 degrees. So this is 14 degrees. So our final answer then, and the last thing we're going to do today, this resultant vector r is 335 kilometers an hour. Okay. And we're traveling at north 14 degrees west. Now, some people are saying you could have west, okay, and 90 minus 14, 76 degrees north as well. If you were to draw it sideways and then up. Both of these are correct. You don't have to write both of them down, only have to do one. Okay, in the essence of having some time to think and process, I'm going to stop there today. Okay. Any general questions from anybody online or in the room that you want to ask me before we're going to do some more practice on this tomorrow. I'll give you a couple to do and we'll go through them and stuff like that. Any questions before I let you go? Okay, come on in. Hopefully it'll be a better connection tomorrow morning. I'll be online here. Hopefully everything was clear, but I'm going to log out and we'll see everybody tomorrow. Somebody want to go get the door? See who that is? All right, see you guys. I'll be putting this up on the site as well so that you can look back on it if you want. All right, see you guys. Bye-bye.